Welcome to CW 5.8. Today we're going to talk about a new function called the logistic function. And it's a pretty interesting function. It's modeled right here, and the graph is right here. And as we talk about it, you'll quickly see why it's relevant to the world today. The function below describes the number of people, f of t, who have become ill with influenza a few weeks after its initial outbreak in a town with 30,000 inhabitants. So I'll highlight that. How many people became ill with the flu when the epidemic began? So the graph is shown right here, and you're going to see something pretty interesting. Notice how there's an asymptote right here and right here. So it actually has two HAs, which makes it pretty unique. So for now, let's just figure out this question. When it began, how many people were ill? So we're looking for this point right here. That's like your initial point, or think of it as your y-intercept. So to find that, we're going to let t equal 0. So you will need your calculator for this lesson, but for this particular problem, you're going to notice something pretty interesting. When I plug in 0, this will become either the 0, which is simply 1. So really we get 30,000 over 21. And then we plug that in your calculator, and you're going to get roughly 1,429, and then we'll put people. So that's going to be how many people became ill when the epidemic began. Now it says how many people were ill by the end of the 4th week. So simply let t equal 4. F of 4, that's equal to 30,000. And that's going to be 1 plus 20 times e to the negative 1.5 times 4. Now when you put this in your calculator, you want to make sure you put this times in front of the e. The calculator does not like it when you leave that out, so make sure you put, again, this times right there, and that should make sure the calculator calculates it for you. Now we estimate it, and we get about 28,583 people. If you look at this graph, it makes sense why there's two asymptotes, because if you look at this right here, this horizontal asymptote, that would be y equals 0, which makes sense because we can never have a negative amount of people being sick, right? So this graph is just going to continue on like this, because it really shouldn't ever be down here. And up here, this is going to limit how far the infection can go. So in our problem, this value is going to be y equals 30,000. And that would be because, look at this, there's only that many people in the town. So that's kind of like your max people getting sick. So if we look at part C, what is the limiting size of the population that becomes ill? That's like saying, what's the most people that could get sick? And that would be right there. You can look at the graph, that's 30,000. So now we can do some limits with this. So for this one, we can look at the graph, and we're going to quickly see that if you plug in infinity, this is 30,000, and if you go to negative infinity, that'd be 0. But we definitely want to make sure you understand it just numerically. So let's try the brute force method here. We're going to plug in infinity. And notice what happens. You get 30,000 over 1 plus 20 e to the negative infinity. That would be 30,000 over 1 plus 20 over e to the infinity. This thing we know goes to 0. So there's our answer, 30,000. By the same reasoning, we can try this one by plugging in negative infinity. And let's see what happens here. 1 plus 20 e to the positive infinity. Now this thing right here, that's just a giant number. That's basically 30,000 over infinity, which we know is going to trend towards 0, and there's our 0. That's it.